Hi everybody, this is Dr. Tausman coming to you live from my house in Roanoke, Virginia. The recording that we're having for today is the recording after the first test. This will be due on, June 22nd. Hope the first test was good for you. I'm going to assume that you picked up the knowledge that the first test had, and we'll just move forward at this point. So if you pick up the agenda and you have your textbook as well, that's what we're going to cover here. General information. So you have the case study before you about a new drug that reduces pain. Give the drug to 3 people, rate their pain 1 hour later, and 3 other people, I don't. The question is the drug actually working? Does it cause a statistically significant improvement in pain levels? So for the 3 people that get the drug, the scores are 1, 2, and 3. A higher score means more pain. For the 3 people that don't, they get scores of 5, 6, and 7. And the first question we have to ask after the question about the drug significantly reducing pain is, what kind of formula can we actually use on this particular data set? Now, if you remember in the past, we have used the z-score formula. The z-score formula we would not be able to use in this particular case. And I'm wondering if anybody has any thoughts on why you cannot use the z-score formula here. Well, the main problem is, if you remember back when we were covering the z-score, the whole assumption of using the z-score is you had to know information about the population. If you remember those problems, we had situations where it was the SAT situation, IQ, and in those situations you knew what the population had normally done. With the t-test and with most statistics in psychology and behavioral sciences, you know nothing about the population. In those cases, remember, with the IQ and the SAT, we knew things about the population. We knew mu and we knew sigma. But in most cases in psychology and in behavioral types of research in social sciences, we know nothing about the population. We do not know mean or mu, and we do not know sigma. So instead, the first useful statistic that we're going to cover in this class is the t-test. You can do the t-test when you don't know anything about the population. And so the t-test is kind of an interesting situation. What we generally do, because we don't know anything about the population, is in the numerator we take the mean of how the drug works how pain is without the drug, and we subtract it from how pain works when you have the drug. And if you turn to page 317, there's a big picture on 317, 10.2. We use the samples to estimate the treatment effect. We use the sample of the first group, sample A, and the second group, sample B. What we're really interested in is the populations that both of those came from. And so the numerator for the t-test is the idea of, is population A significantly different than population B? We use the sample means, x bar 1 and x bar 2, to represent that. So the idea here is to assess, is there a treatment effect there? So that is the numerator. Is there a treatment effect? And it's very easy to compute that, because if you look at this particular problem, the mean of the people without the drug, with 5, 6, and 7, the mean is 6. The mean of the 3 people that get the drug, 1, 2, and 3, is 2. So the numerator is very simple to compute. The treatment effect, hopefully you can figure this out, is 6 minus 2. So the numerator is 4. And it's the difference between the sample means. The sample means are our best guess for what the true populations are in this particular case. So hopefully that makes good sense to you. Now, the denominator. Oh my God, the denominator. If you remember back to the z-test, the denominator was the idea of the standard error of the mean. You kind of get the standard deviation and you divide it by the square root of n. And you want anything that's standard error of the mean to be small. That's the goal. Unfortunately, in this particular situation, the standard error of the mean for the t-test gets very, very complicated. If you look at that formula, with the denominator of the t-test, sp, 1 divided by the square root of n, plus 1 divided by the square root of n, 3 sigma, and then sp, holy Toledo. If you turn your book to page, what would it be here? If you turn your book to page 325, you can see that I'm not making this up. The standard error of the mean gets very, very complicated. That's the bad news for you. The bad news is that the standard error of the mean is very, very complicated. The good news is most of the statistics done on the t-test, you can rely on a computer to do most of these statistics. The denominator really boils down, if you move down on your agenda, to C, the standard error of the mean. You just get that. The statistics are usually done on the computer, and they give you what the number is. That is basically the discrepancy between the sample mean and the population. You want that number to be low, and in this particular class, we're not going to waste our time trying to compute that a gazillion times. So the t-test formula is very similar to the z-test. It's the differences in the mean, as reflecting the differences in the population means, mu's, and the denominator is the standard error of the mean. We don't have to go through all the book computations because computers usually give us the formulas for this, and they also compute it. We just have to understand basically what it means. So hopefully you understand that and it's working for you. Let's actually go. Actually, I'll stop the recording here and move on.